You know that little microchip in your phone? Well, it all started as just an idea. But how in the world does a simple thought become a real, physical object with billions of tiny parts? It's a journey from pure imagination to atomic level engineering, and we're going to break down how it all works. Right, so how do you actually get from a concept, say, I want a faster graphics processor, to a tiny piece of silicon just packed with billions of transistors? Well, it turns out it's one of the most intricate manufacturing processes we've ever come up with. I mean, the scale of this challenge is just immense. We are literally talking about messing with physics at the atomic level, juggling these huge, complex supply chains, and solving design problems so tricky that no single person could ever hope to tackle them alone. So, how do you even begin to tackle a problem that seems impossible? Well, it's the same way we've been doing it for centuries. You just break it down. Engineers have this brilliant strategy they call divide and conquer. They take the whole massive job of designing and building a chip and chop it up into smaller, much more manageable steps that they can handle one after the other. When you really look at it, this whole incredible journey basically boils down to a three-stage process, and each stage is a huge leap, right? It takes the idea from this world of abstract concepts and brings it one giant step closer to the physical world of actual atoms. Okay, let's take a look at the roadmap for this whole thing. First up, you've got system design. This is where the big idea gets turned into a technical specification, using a special language just for hardware. Then, we move into logic and physical design. This is where that spec gets translated into a super detailed geometric blueprint. And finally, you have fabrication. This is where a specialized factory, what they call a foundry, takes that blueprint and physically builds the chip. Now, for this whole divide and conquer thing to even work, engineers lean on one absolutely crucial concept to manage all that complexity. And that concept is called abstraction. So, what exactly is abstraction? Well, to put it simply, it's basically the art of hiding all the nitty-gritty details you don't need to worry about just yet. This lets you focus on the big picture, the system and what it's supposed to do without getting totally bogged down in the billions of tiny components that will eventually make it all work. And what's really fascinating here is how the level of abstraction changes as you go through this journey. At the very beginning, during system design, you're way up high, looking at the big picture, focused on what the chip needs to do. But as you get closer and closer to actually making it, that level of abstraction drops. You start zooming in, adding more and more detail, first logic gates, then transistors, and eventually the final, super detailed physical layout. So yeah, the entire design flow is really just a journey from high abstraction all the way down to low abstraction. You start with a simple idea, and you just keep piling on layers of detail until you have this complete, perfect blueprint that's ready for the factory, with every single tiny detail accounted for. Okay, so right at the very beginning of this journey, when we're at that highest level of abstraction, engineers have to make a really critical decision. It's a choice that's going to affect everything else that comes after. They have to figure out what parts of the system should be built as physical, dedicated hardware, and what parts should be flexible, programmable software. And believe me, there's a huge trade-off here. On one hand, you've got hardware. It's blazing fast because it's custom built for one specific job. But, and this is a big but, it's totally inflexible. A bug in the hardware? Whoa, that is super expensive and difficult to fix. Then you have software. It's a bit slower, sure, but it's incredibly flexible. You can update it, you can change it, you can patch bugs, no problem. Okay, I know this might sound a little abstract, so let's bring it back down to earth with a perfect real-world example, something that's literally happening inside your device as we speak. Video compression. Whenever you're watching a video, there is a ton of complex math going on behind the scenes to make it all work. So what engineers do is they find the main bottleneck in that whole process. The one single task that's eating up most of the computing power. For video, it's a really complex calculation. So what do? They build a dedicated piece of hardware, they call it a hardware accelerator, to do just that one job. And because it's custom built, it is incredibly fast. Meanwhile, everything else, like managing the video frames, stays in flexible software that can be easily updated. It's truly the best of both worlds. So, you see how it all comes together? By breaking the problem down into manageable chunks, by using abstraction to wrestle with all that complexity, and by making those really smart choices between hardware and software, engineers can actually turn a simple idea into a physical reality. And really, that's the magic of it all. This superstructured, step-by-step process is what lets us tame that unbelievable complexity. It's the bridge that connects our imagination to the atomic-level precision of a modern microchip. It is, quite literally, how an idea becomes a thing. And all of this leaves us with one last, really fascinating question. Right now, as we speak, brand new ideas for AI, for quantum computing, for technologies we can't even dream of yet. They're all just starting out on this exact same journey. So you have to wonder, what will they become when they finally reach the end?